lesson we are going to discuss the Euler's form of representation of a complex number. So let us revisit all the forms that we have done till now. So x plus iy was the Cartesian form of representation. We also found that from the Cartesian form I can find the length of the complex number or the modulus of the complex number, and we can find the argument of the complex number, which is like the direction of complex number with respect to the positive real axis. Using this, I could write the polar form of a complex number as r cos theta plus ri sin theta, right? This is called the polar form of representation, and we could see the conversion from one form to another. We knew what it was because r is nothing but the modulus and theta is nothing but the argument. We will now look at the third form of representation, which connects exponents to trigonometry by saying that e raised to I theta is same as r cos theta plus I sin theta. Okay, so to understand this, let me show you a demonstration using Desmos. So I have a circle here of radius 1. I made radius 1 so that I'm not worrying about the modulus. Okay, so modulus is 1 and argument is some theta. Okay, so let me write down that complex number for you. So I have argument of 1 and angle of theta. So my complex number is cos theta plus I sin theta. I don't need to write r because r is 1. And as per this representation, it is going to be ei theta because r is 1. And I want to show how these two are equivalent to each other. Correct? So let's go back to our Desmos and see. So the first thing is I'll take theta as 0. So cos of 0 is 1 and sine of 0 is 0. So the number should be on the real axis, correct? So this is my e raised to 0, and e raised to 0 is also 1. So left hand side is 1 and right hand side is also 1. So my number is on the real axis with a magnitude of 1. So there is a resemblance. If I change the value to 1, if I change the theta to 1 radian, then where according to the trigonometric ratio, where should it be? It should be at distance of the x value, x coordinate should be at cos 1 and the y coordinate should be at sine 1. And if I take the value of e raised to 1, it is coming to the same thing, e raised to 1, and that's why it is being represented as e raised to I because the modulus, so it is rotating. If I say from e raised to 0i to go to e raised to I, it rotated by a magnitude of 1 radian. That's what e raised to I is representing. Now what if I make the value of a something else, right? If I'm making the value of this angle as 2, where will it go? So it has to be cos of 2 and sine of 2. And it is now showing as e raised to 2i. The value of e raised to 2 is same as the value that I would get with cos 2 and sine 2. If I'm making a3, if I'm making a4, if I'm making the angle 5, and if I'm making the angle 6, it seems like it is rotating the same way as when theta is rotating. I'll use my representation here also to show you. If I think of e raised to I, okay, which I could show you, e raised to I is cos of 1 plus I sine of 1. After that, e raised to I raised to theta, meaning how much ever the angle is rotating by, I can think of the left hand side as e raised to I getting multiplied with itself, repeated multiplication theta times, isn't it? Isn't that what exponents say? E raised to I raised to theta means e raised to multiplied itself how many times? Theta times. And what happens when the indices with the same base are getting multiplied, what happens? The indices get added. So if it is multiplied 2 times, means the angle is changed to 2 radians, I'll get e raised to 2i. If I change the angle to 3 radians, I'll multiply it 3 times, I'll get e raised to 3i. If I multiply it theta times, I'll get e raised to theta I. So that means how much ever I rotate the angle by, that much is how the e raised to I is also being raised to. So I'm seeing an equivalence, and now if I look at some specific points, okay, if I make them as pi by 2, let's look at the thing again. If I'm making the value of theta pi by 2, see where the point is. Cos of pi by 2 is 0 and sine of pi by 2 is 1. So it must be on the imaginary axis, and e raised to pi by 2i is at that point. If I make that as minus, if I make it as pi, do you see? E raised to I pi. Cos of pi is minus 1 and sine of pi is 0. So I should be on the minus 1 point. And that's where I am. And it also reminds us of the very famous formula. If e raised to I theta is cos theta plus I sin theta, if I'm able to see the resemblance, when theta is pi, I will get e raised to I pi is equal to minus 1, which is e raised to I pi plus 1 equal to 0. This is the famous Euler's formula, and this comes from the Euler's form of representation of a complex number. Now we are able to understand that when the angle is changing, it's like I'm moving on a circle with radius of r. I have taken r as 1 to simplify the situation. But otherwise, every complex number of the form e raised to I theta or r cos theta plus I sin theta is like movement along the circle of radius r. Theta is the angle at or the direction of orientation of the point with respect to the real axis. So that is how I am able to understand this form, and now you may see the entire movement. Do you see how when angle is changing, the points are moving along this? After every 360 degrees, you are also seeing that the point is coming back to the original point and then moving again. Do you see that? So it is very similar to later when you study trigonometric ratios also. You will revisit this idea on the unit circle, and you will see a lot of resemblance in what we said now with what we will be studying later as well. So that's why Euler's form is correct. That means I don't need to worry about why there is a format. Now also, what is the use of this Euler's form? Is it really useful? Why should I know this? Let us look at some of the multiplication and product rules in the next video, and you will realize how it is useful. But before I go there, let's write down some numbers in all the formats. So 1 plus I, modulus is root 2. Now you can use your calculator, so I'm going to assume you will be able to see or validate what I am writing as the answers. In the polar form it can be written as this, and in the Euler's form it can be written as this. Correct? Let's write down another number, 3 minus 4i. The modulus is going to be 5. The argument is in radians I am writing. It is cos of 0.927. I am looking at the 3 significant figures. Sine of 0.927, and in the Euler's form I can write it as 5 e raised to I 0.927. Correct? 5 is the modulus and that's the argument. Or I can also write it as 5 cis 0.927. Okay. So any complex number that you have. Also some special numbers, like I have cis pi by 2, which is nothing but e raised to I pi by 2. Cis of pi is e raised to I pi, just to show you the equivalence. Okay, if I have only, and cis of pi means what? I'm having only a real number, no imaginary part. So pi by 2 means what? Only imaginary number, no real number. This is only real number, no imaginary number. If I have 3 times this of minus pi by 2 means what? Only imaginary number, no real number. E raised to 3 times e raised to minus I pi by 2. So do you see how we are drawing equivalence to the Cartesian form, to the polar form and the Euler's form? It's important that you are able to change from one form to another, because sometimes you will need the Cartesian form, sometimes the polar form, and sometimes the Euler's form. Now the conjugate, also important to know. Conjugate x of x plus iy is x minus iy. In the polar form it is written as r cis minus theta, or r cos theta minus I r sin theta, and in the Euler's form it will be written as r e raised to minus I theta, the conjugate. Okay, I shouldn't be writing equivalent, I'm talking about the conjugate. The conjugate is written as this, and in the polar and Euler's form the conjugate is written this way. Correct? The angle is changing to negative because it's a symmetry above the x-axis. Now with this kind of readiness, we will be able to look at products, quotients and powers in the polar form and the Euler's form in the next video.